Now, in this video, we look at a few test questions on the OTTO cycle. But before that, we explain it briefly using the PV diagram to help our understanding of the full cycle. Now, let's look at the OTTO cycle, and let's consider this PV diagram to represent it. Now, the OTTO cycle is an ideal model of the thermodynamic process in a fuel engine. Now, thermodynamic processes looks at changes in the physical state of the system in terms of its temperature, volume, and pressures, which is caused by transfer of heat energy and work done by the system or on the system. Now, let's start at point A, where a mixture of fuel and air has entered the cylinder. Now, in this model, the air-fuel mixture assumes to behave as an ideal gas. It neglects friction and turbulences and loss of heat to the cylinder wall, and many other effects that combine to reduce efficiency. And so here we are looking at an ideal model of a thermodynamic process. So in the step A to B, the mixture is compressed adiabatically. So here the volume of the system decreases, intermolecular distance decreases, the frequency of collisions also increases, the energies of the molecules increases, causing an increase in the pressure of the system and also an increase in the temperature of the system. So volume decreases, pressure increases, and temperature also increases. So now these combined conditions generate favorable conditions for ignition. And because A to B is an adiabatic process and compressing the system involves effort, work is done by the surrounding on the system. So work done is negative. Q is 0, as the process does not involve heat change. Now, the step B to C involves constant volume. So this is an isochoric process. Now, in this step, pressure increases and temperature also increases. And the increase in temperature is a result of the heat absorbed by the system at the end of the adiabatic process A to B. Because the conditions generated in A to B causes ignition. And this ignition releases energy which is absorbed here by the system. Now, the step C to D is an adiabatic expansion process. Now, with adiabatic processes, Q is 0, and here work is done by the system on the surrounding during expansion. So work done is positive. There is an increase in the volume, decrease in the pressure, and decrease in temperature. So this temperature decrease results in loss of energy, which occurs in the last stage of the cycle, D to A. So energy is released from this stage as pressure and temperature decreases. And this occurring under isochoric conditions of constant volume. Now, there are some equations that we need to take note of in the OTTO cycle. Now, for the adiabatic processes, which means that the temperature at A and the volume at A is equal to the temperature at B and the temperature at C, the volume at C is equal to the temperature at D. Now, let's be familiar with this also. And efficiency of the OTTO cycle, let's denote by the letter N, is given as where R is the compression ratio. Now, the step B to C occurs under constant volume, and under constant volume, no work is done by the system or on the system. So the energy received by the system goes to increase its internal energy, where its internal energy is also given by the formula and the energy lost by the system causes a decrease in its internal energy and given by the formula but since this amount of energy is lost by the system, it causes a decrease in the internal energy of it. Now let's try a few questions. Now let's look at this question. What is the compression ratio of an OTTO cycle that has an efficiency of 46% and a gamma ratio of 1.4? Now we are going to rely on this equation. Let's represent by the letter N. It's giving us where R is the compression ratio that we are expected to determine. So our efficiency now let's rewrite this ratio. Let's take this to the left and bring this N to the right. Which means that this can also be rewritten as 1 minus N over 1. Now, if we are to reciprocate this expression over here, we're going to have and if we are to exponentiate this expression, we're going to have this. And so that will mean that we can represent the compression ratio in the form so in this state, we can now plug in the figures or the values to determine the compression ratio of the OTTO cycle. Now, our efficiency is given as 46%, which is 46 over 100, and that is 0.46. In the question, our gamma has been given as 1.40. So this implies (1.40 minus 1), we have 0.40. So our compression ratio is given us and 1 over 0.40 is 2.5. So R is given as so our compression ratio for this OTTO cycle is 4.67. Now the compression ratio of a standard OTTO cycle is 10. We have been given the pressure and the temperature at the beginning of the compression. The heat transfer to the air per cycle has also been given as 1,800 kilojoules per kilogram. Gamma has been given and we are asked to determine the pressure and temperature at the end of each process of the cycle. Now, first of all, let us draw the PV diagram to help us visualize the process during the cycle. Now, the y-axis to represent our pressure and x-axis our volume. Now, let's label this 1 and the direction of the cycle. Now, from the question, we have been given the following data. Our pressure and temperature at the beginning of the compression has been given. So T1 we convert it to Kelvin by adding 273. Our P1 which is the same as 100 kilopascal. Now our QH is giving us 1800 kilojoules per kilogram. Which is the heat energy absorbed by the system at this step of the cycle. Now, gamma is giving us 1.40. Now, 1 to 2 is an isentropic process, and here the ideal gas law can be applied, in which case T2 over T1 is giving us Now, let's take note of the fact that V1 over V2 is referencing the maximum and the minimum volumes, which is equivalent to our compression ratio. Now, in the question, our compression ratio has been given as 10, so R is 10. That means V1 over V2 is equal to 10. So T2 is giving us and plugging in the values, we're going to have T2 as V1 over V2 is giving us 10. Gamma is 1.40 minus 1 is 0.40. Now, if we are to do the mass, is giving us, so T2 So T2 is 723.4 Kelvin. Now, to determine P2, we apply this ideal gas relation between pressure and volume, giving us so P2 takes the form, and when we are to plug in the values, we're going to have now V1 over V2 is equivalent to the compression ratio, which is 10, and our gamma is 1.40. Now, 10 exponent 1.40 is giving us now, if we are to plug it in P2, so then we're going to have P2 as kilopascal, approximately 2511.9 kilopascal. So now let's determine the pressure and temperature at point 3. Now, the heat energy absorbed by the system is given by the formula now, because we're dealing with an air standard OTTO cycle, let's assume 1 mole. Now, QH has been given in the question as 1,800 kilojoules per kilogram. And let's consider our molar specific heat as 0.718 kilojoules per Kelvin. So with this, we can say that so T3 will be giving us and when we are to plug in the values, T2 has already been determined earlier as 723.4 Kelvin. So that means T3 will be given as so T3 is 3230.4 Kelvin. Now, point 2 and point 3 have the same volume because the process 2 to 3 is an isochoric one, also sometimes referred to as isovolumetric process. Now, if we are to apply the ideal gas law, but the volume at point 2 is equivalent, is the same as the volume at point 3. So we're going to have so this implies our pressure at point 3 is given by and if we are to plug in the values, T3 has just been determined. And T2 has been determined earlier as 723.4 Kelvin. And if we are to work it out, we're going to get the pressure at point 3 as so that is the pressure at point 3. Now, for the B part of the question, what is the net work output? For our overall energy balance, so our net work output is given by, now QH has been given in the question as 1800 kilojoules per kilogram. And QC can be determined by the formula where T1 and T4 are the final and the initial temperatures for the final step of the cycle 4 to 1. Now showing it on the diagram, so our QC is given as so we're dealing with an air standard Otto cycle, so N representing the number of moles is considered as 1. And our CV is given as 0.718 kilojoules per kilogram per Kelvin. So let's determine QC, and then we can go ahead to determine our net work output. So for the B part of the question, So it means that the system loses per cycle this amount of energy. So our net work output so it means that so 1,800 kilojoules is absorbed by the system, 1,083.4 kilojoules is used to do work, and 716.6 is considered to be the unused amount of energy or lost by the system. Now, the C part of the question is to determine the thermal efficiency. And we can do that in two ways. First of all, efficiency, let's denote by the letter N, is given as, for the Otto cycle, is given by this formula. Alternatively, let's denote this by the letter E, is given by so with our C, E is (60.2% efficiency. Now, alternatively, we could determine the efficiency using this formula here. Our compression ratio is 10, our gamma is 1.4. So we're going to have approximately 60.2% efficiency. So our Otto cycle operates at an efficiency of 60.2%. Now, with the D part of the question, we are to determine the mean effective pressure. Effective pressure is given by now, where the mean effective pressure is theoretically the average pressure acting on the piston, and V1 minus V2 is our displacement volume during the entire power stroke, and our W is our net work output. Now, for our ideal gas equation, we have where R is the universal gas constant. In this question, we're dealing with an air standard Otto cycle. So we are not going to use the universal gas constant, but we are going to use the specific ideal gas constant specific to air. So R, in this instance, will be considered as 0.287 kilojoules Kelvin. If the question were not to be specific, then we would have used our universal ideal gas constant, which is our universal ideal gas constant. But for this question, we're going to use the ideal specific gas constant for standard air. So for the D part of the question, we say that we know of the net work output. So let's determine the volume at point 1 and point 2. Now, at point 1, now we assume N is equal to 1 because we're dealing with air standard Otto cycle. So our volume is going to be given as temperature at point 1 is 288 and pressure at point 1 is 100 kilopascal, and V1 is equal to 0.827 meter cubed per kilogram. It's referred to as specific volume, which represents the volume occupied by 1 unit of the mass. Now, Kelvin cancels out Kelvin. Now, joules is a measure of energy expressed in Newton meter, and Pascal is a measure of pressure expressed in Newton per meter squared. So this expression over here comes up to meter cubed per kilogram. That is why we have as the units for V1 meter cubed per kilogram. Now there's a relationship between V1 and V2 given as the compression ratio, which is 10. So V2 can be determined as 0.0827 meter cubed per kilogram. So with V1 and V2 determined, we can now determine the mean effective pressure. So our kilogram cancels out, and we're going to have so our mean effective pressure is 1,456 kilopascal. So that is our answer. Now, what is the theoretical efficiency of an Otto cycle engine with gamma 1.40 and with a compression ratio of 9.50? Let's denote by N, where R is our compression ratio. Now, our gamma is given as 1.40 and our compression ratio is given as, so now we can now plug in the values. Now, if we are to simplify, we're going to get, now our denominator reduces to, so we're going to have 4065, and we're going to have 0.5935. So the efficiency of this Otto cycle is approximately 59.4%. So let's look at this question. We have been given the gamma as 1.40 and the compression ratio as 7 for an Otto cycle, and we are expected to determine the temperature at the end of the compression stroke. Now, let's try to sketch this. Pressure on our y-axis and volume as our x-axis. Now, we start at A. This are points B. We consider this as our point C and our point D. Here is 0, and this is the direction of Now, this question relates to the step AB, which is an adiabatic compression process. The gasoline-air mixture enters the cylinder at point A, and we have been given that the temperature at this point is 22 degrees Celsius. We are expected to determine the temperature at point B, which is the end of the compression stroke. Now, the governing relation to consider is now, let's take note that the volume of the system at point A divided by the volume at point B is equivalent to our compression ratio R. Now, the question provides that, and we're going to convert this to Kelvin, and we're going to have our gamma has been given as 1.40, and our compression ratio is 7. So we plug in these values into this equation. And when we compute, it's approximately 2.18. So we're going to have approximately 643 Kelvin. So we convert this to Celsius to have our temperature at the point B that is approximately 370 degrees Celsius. So that is our answer.